Welcome back to Ancient Earth Documentary Podcast. Listen, 4,540,000,000 years ago does not feel real. It does not feel like a time exactly. It feels more like a number that got too big and floated away from meaning. But that number is where our story starts. In a place that was not yet here, with materials that were not yet us, before planets, before the moon, before anything solid enough to call a world, before anything we would recognize as order or structure or stability. There was chaos, pure, unthinking, violent chaos, and somehow, out of that chaos, everything we know emerged. Not in a gentle way, not in some orderly, predictable sequence laid out like a textbook with clear chapters and logical progression, but through collision, pressure, and the kinds of impacts that would obliterate entire civilizations before they even existed to be obliterated, before humanity existed, before life existed, before Earth was even fully formed. So take a moment before we start, settle in, and understand what you are about to hear. Because we are about to travel backward through time to witness the moment the solar system was still a war zone, when gravity was the only law and violence was the only language, when destruction and creation were the same process, when chaos built order. This is not a story about stability. This is a story about the moment stability did not exist. This is the moment everything was beginning. Imagine a cloud. Not the fluffy kind floating across a summer sky. Imagine a cloud that is incomprehensibly massive, stretched across light years of space, rotating slowly, made of dust so fine it defies description and gas so cold it would make modern physics uncomfortable. Imagine material so diffuse that it is barely a cloud at all, barely a thing, just a thinning of the void where particles exist but space still dominates. This was the solar nebula. Around 4.6 billion years ago, somewhere in the Milky Way galaxy, part of a giant molecular cloud began to collapse under its own gravity. And when we say collapse, we do not mean a gentle settling or a slow compression. We mean something catastrophic, not gradually, not gently. A shock wave from a nearby supernova explosion probably initiated this collapse, a sudden shove that destabilized the balance holding the cloud together. The energy from that explosion, traveling outward, hit the molecular cloud and disrupted whatever equilibrium was maintaining it. Suddenly, the gravitational forces that held the cloud suspended in space became overwhelming. The cloud could no longer support itself. It fell inward. Imagine a wall of pressure moving inward from all directions simultaneously. Imagine material being compressed continuously, relentlessly, with nowhere to escape. Most of the collapsing mass collected in the center, forming the sun eventually, while the rest of the material flattened into something resembling a disk, rotating faster as it compressed, the way a figure skater spins faster when pulling in their arms. Physics has these elegant demonstrations, and this is one of them. Conservation of angular momentum. The cloud was already rotating slowly. As it compressed, that same rotational velocity increased, faster and faster. A thin disk formed, rotating rapidly around the hot, dense center. This disk, this rotating cloud of remaining debris, was the protoplanetary disk. And this is where everything came from. Every atom in your body, every molecule in the earth beneath your feet, every element in the vast solar system came from somewhere in this rotating disk. The materials that would become planets, moons, asteroids, comets, and eventually life itself were scattered throughout this rotating envelope of dust and gas. The disk was not uniform. It was never uniform. It had variations in density, temperature, and composition. These variations mattered immensely. They would determine what kind of planets formed in different regions. They would shape the future solar system in ways that were already encoded into this primordial disk. Scientists now believe that a mysterious gap existed in this protoplanetary disk around 4.567 billion years ago. This gap was real. It was not the boundary between regions, but an actual absence of material, a dividing line in the disk. This gap likely served as a cosmic boundary, keeping material on either side of it from interacting easily. Material could not cross this gap easily, a physical separation that would shape the entire future composition of our solar system. Think about how significant this is. A gap in the disk, early in the solar system's history, would create two distinct regions with different compositions. On the inner side of the gap, closer to the young sun where temperatures soared to thousands of degrees, dust and gas coalesced into small, rocky materials. Materials with high melting points: iron, nickel, silicates. These terrestrial materials would eventually form Mercury, Venus, Earth, and Mars, the rocky planets we know today, small, dense, close to their star. On the far side of the gap, much farther from the young sun, where temperatures plummeted to hundreds of degrees below zero, a completely different kind of material gathered. Volatile compounds, water ice, methane ice, ammonia ice, carbon dioxide ice, materials that would remain frozen, at least in the solar system's early history. This is where the raw ingredients for Jupiter, Saturn, Uranus, and Neptune accumulated, materials that would form the gas giants in their vast orbits, capturing hydrogen and helium directly from the nebula. One planetary scientist explained it clearly. Crossing this gap was not easy. A planet would need an enormous amount of external torque and momentum to break through. A planet would need to be pushed by something immensely powerful. This gap essentially restricted where planets could form, dividing the solar system into two fundamentally different regions. This explains everything about modern solar system architecture. The evidence for this ancient boundary persists today, billions of years later. It explains why the inner solar system contains small rocky terrestrial planets, tightly packed, relatively close to the Sun. 4 small worlds: Mercury, Venus, Earth, Mars. Similar in composition, similar in size, crowded into a small region of space. And the outer solar system hosts massive gas and ice giants far away, in the cold reaches where sunlight barely warms the freezing materials. These are Jupiter and Saturn, enormous, and Uranus and Neptune beyond them, cold and distant. The gap created this architecture. The gap encoded into the primordial disk where planets would form. This ancient boundary, mysterious and fundamental, remains one of the greatest achievements of planetary science, explaining how the solar system organized itself billions of years ago. The implications stretch forward to this day. Why are the terrestrial planets small and the gas giants massive? The gap. Why is the asteroid belt depleted and relatively empty? The gap. Why does Earth orbit in the region it does, in the zone it occupies? The gap, and everything that followed from the gap. But here is the thing about the protoplanetary disk that matters most beyond the gap. It was not peaceful. The disk was chaotic, densely packed, and every object in it was constantly colliding with every other object. The disk was a war zone, and that war was about to intensify. The protoplanetary disk was a place of action. Things were happening constantly. Change was the only constant. The slow collapse that had created the disk was transitioning into something faster, something more violent, something more transformative. The young disk was not settling into stability. It was accelerating toward chaos. And the chaos would build the worlds. Somewhere inside this chaos, the sun was being born. And it was not born gently. Over the first 100,000 years of the solar system's existence, the molecular cloud continued collapsing under its own gravitational pull. Imagine the pressure, the compression, the relentless inward crush of gravity acting on trillions of tons of material. The materials compressing at the center grew hotter, denser, more concentrated by the second. Gravity was relentless and patient. It pulled inward from all directions simultaneously. Gravity does not tire. Gravity does not negotiate. It just pulls. The temperature at the core began to climb steadily, then rapidly. Pressure mounted exponentially. Atoms that had been separate for millennia were forced together at ever-increasing density. Electrons were stripped from their atoms. Plasma formed. The young sun, this proto-sun, a cumular, TED material, continuously through this entire period. It was not yet a star. A star requires fusion. This was just a hot, dense clump of collapsing material, growing larger by pulling in everything around it through gravity. A failed star, or rather, a star in progress. The baby sun kept accumulating material for roughly 50 million years. 50 million years. This timescale is almost unimaginable. 50 million years of continuous growth, pulling material inward, compressing, heating, concentrating everything at the core. The proto-sun grew. It became hotter. It became denser. The pressure at its center reached extremes. But something had to give. Something had to break. Or more accurately, something had to ignite. Eventually, at some point, the temperature and pressure at the core is so intense, so utterly extreme, that atomic nuclei began fusing together, not colliding and bouncing apart, not even colliding and sticking, but actually merging. Hydrogen, the simplest and most abundant element in the solar system, began fusing into helium. Hydrogen nuclei, single protons, were forced together with such violence that they merged. This nuclear fusion released energy, not chemical energy, not thermal energy, but the binding energy of atomic nuclei. The energy released when mass itself was converted to energy through Einstein's equation. This was not controlled fusion like in modern laboratories on Earth. Carefully managed, contained, slow. This was violent, explosive, spontaneous fusion ignited by the crushing weight of the proto-sun itself. Imagine the intensity. Imagine the temperature required. Imagine the pressure needed to force protons together against their electromagnetic repulsion. And yet the proto-sun created exactly these conditions. Hydrogen fusion released tremendous amounts of energy. Enormous amounts of energy. Imagine an explosion so large it could power a star. And then imagine that explosion continuing indefinitely. Enough energy to counteract the sun's own gravity and prevent it from collapsing further. This is the critical moment. This is where the process of gravitational collapse halted. This process stabilized the young star. The outward pressure from the fusion reactions balanced the inward pull of gravity. An equilibrium emerged, a delicate balance, not stable in the sense of unchanging. Stars are never unchanging, but stable in the sense that a new process took over. Gravity still pulled inward. Fusion still pushed outward. These two forces, perfectly balanced, created a star. The sun ignited, became luminous, became the star we know today. A main sequence star, a hydrogen-fusing star, a star capable of sustaining this process for billions of years into the future. This balance would persist, or a long time, not forever, but for an incomprehensibly long time by human standards. Billions of years. During all those billions of years, the sun would remain relatively stable. It would not suddenly expand. It would not suddenly contract. It would not burn out or dim dramatically. It would persist. It would endure. It would continue to fuse hydrogen into helium at a relatively steady pace. The sun had found its equilibrium and would maintain that equilibrium through the patient action of nuclear fusion balancing gravitational collapse. This stability was essential. Without a stable star, the surrounding disk could not have formed stable planets. Without a stable star, there would be no reliable source of heat and radiation. Without a stable star, the chemical and thermal conditions necessary for planet formation would not exist. The sun's stability was the foundation upon which planetary formation rested, but the ignition had immediate consequences. The intense energy released by the newly fusing sun created pressure that pushed outward against the rotating disk of remaining material. This outward radiation pressure pushed against the disk. This pressure prevented the sun from accumulating more material. The star had stabilized itself, and in doing so, had also finalized the amount of material available to build everything else. There would be no more material captured by the sun. Whatever remained in the disk, whatever particles and planetesimals would eventually form, would have to do so from what was left. Planets, moons, asteroids, comets, all the diverse bodies that would populate the solar system, had to be constructed from what remained in that disk. The sun was no longer growing. The sun had stopped pulling in material. And now the disk had to collapse into planets. This transformation from a collapsing molecular cloud to a functioning star happened remarkably quickly in cosmic terms. Perhaps only a few million years separated the beginning of collapse from the moment hydrogen fusion ignited. That speed is part of what makes this period so extraordinary. In 10 million years, the universe went from a slowly rotating cloud to a functioning star. In less time than it takes for humanity to invent writing multiple times, the solar system went from non-existent to partially formed. The universe suddenly produced a star, a heat source, a gravitational anchor point around which everything else would organize. This was the pivotal moment. This was the transformation. This was the instant when the solar system went from a chaotic cloud to an organized system centered on a functioning star. Life, consciousness, possibility itself, all of it traces back to this moment. Not to some gentle emergence, but to a violent ignition in space that changed the rules for everything around it. Not in some poetic sense. Literally, the rules changed. Gravity still applied, but now a star was generating radiation and heat. Now a star was creating a temperature gradient across the disk. The newly formed sun poured energy across the disk. Temperatures soared in the inner regions where the sun's radiation was strongest. Temperatures plummeted in the outer regions where the star's light barely warmed the freezing void. Volatile materials like water, methane, and other ices could not survive in the inner regions. They either vaporized or migrated outward to cooler regions. The inner solar system became the domain of rock and metal, silicates, iron, nickel, materials that could exist in solid form at high temperatures. The outer solar system became the domain of ice and gas, water ice, methane ice, frozen carbon dioxide, materials that remained solid and stable only when cold. This temperature gradient was not accidental. It was fundamental to how planets would eventually form. Everything that happened next depended on this newly ignited star sitting at the center, reshaping the environment around it through heat and radiation. The sun did not just sit quietly at the center. The sun actively sculpted the solar system by determining which materials could exist where. The stellar wind, the outpouring of charged particles from the sun's surface, would eventually blow away the lighter gases from the inner solar system. But that was not yet. For now, the sun was young. For now, the sun was simply organizing the disk through radiation and heat. The disk, now organized by temperature and composition, was ready for the next stage of chaos. And the disk was patient. The disk had time. Millions of years stretched ahead. Billions of years stretched beyond that. Time, in the early solar system, was abundant in a way that humans can barely conceptualize. Time stretched from horizon to horizon. And in all that time, all that incredible expanse of years, the disk would not remain passive. It would become active. It would reorganize itself. It would build worlds. But before planets could form, matter had to consolidate. The disk was not solid. It was a cloud of particles, each one minuscule, separated by vast amounts of empty space. Dust grains, tiny particles, perhaps only a few millionths of a meter across, silicate dust, carbon dust, metal dust. all drifting through the protoplanetary disk. Gravity alone could not pull these particles together quickly at these small scales. Gravity's force decreases with the square of the distance. At the scale of microscopic dust grains, gravity was negligible. The gravitational force between two dust grains was essentially zero, completely insignificant. Two dust grains could drift right past each other without any detectable gravitational attraction, without any force pulling them together. Something else was needed to bring them together. That something else was drag, friction, the collision and sticking of tiny dust grains. This is a process that few people consider when thinking about planetary formation, but it is absolutely fundamental. It is the foundation upon which everything else rests. Without this process, without dust sticking together through collisions, planets would never form. This is not optional. This is not a side process. This is the only way dust becomes pebbles. This is the only way pebbles become planetesimals. This is the only way planetesimals become protoplanets. This is the only way protoplanets become planets. Everything traces back to this simple process. Dust grains colliding, sticking together, forming slightly larger structures. Repeat infinitely. That is how planets are built. That is how worlds are made. Microscopic dust particles drifted through the disk, colliding with each other at relatively low speeds. These were not violent collisions. These were gentle bumps. Particles moving at a few centimeters per second, or maybe a few meters per second at most. When particles collided gently enough, they stuck together. The reasons varied. Static electricity could cause particles to adhere. Chemical bonding at the particle surfaces could cement them together. Mechanical interlocking of rough surfaces could hold them in place. The mechanisms were varied, but the result was consistent and inevitable. Two particles became one slightly larger particle. A dust grain plus a dust grain equals a slightly larger dust particle. These slightly larger particles then collided with other particles. And the process repeated, and repeated, and repeated countless times. This was not rapid. This was not exciting. It was methodical, patient, the slow accumulation of matter through countless tiny collisions. But it was continuous. It was relentless. It was unstoppable. Given enough time, given enough collisions, given enough patience, dust grains would inevitably accumulate. The process did not care about impatience. The process did not care about frustration or desperation. The process just continued. Dust grain by dust grain, particle by particle, accumulation by accumulation. Pebbles began to form after millions of these tiny collisions, each one a collection of billions of dust grains cemented together by impacts and chemical processes. The transformation from dust to pebble was gradual. There was no moment when dust became pebbles. It was not like a switch being flipped. It was a continuous transformation where dust gradually aggregated into larger and larger structures. Pebbles were larger than dust, but still microscopic compared to planets. They were perhaps a few millimeters across, or maybe up to a few centimeters. Some larger, some smaller, but they represented a new phase in the solar system's development. Pebbles were small enough to drift with the disk, moving with the gas and dust, carried along by the protoplanetary environment. But they were large enough to have some cohesion. They were no longer just particles. They were objects. They had mass. They had structure. They were real things. But they were stable. They could survive in the disk without immediately vaporizing or scattering into the vacuum. The radiation from the young sun could not easily tear them apart. The weak gravitational forces at play could not easily accelerate them away from the disk. The disk was now a mixture of dust and pebbles, with pebbles becoming more common as the accumulation process continued. The disk was evolving. It was changing. It was transforming itself through the simple, relentless action of collisions and accumulation. The proportion of dust to pebbles shifted gradually. More pebbles formed. Fewer isolated dust grains remained. The disk became denser. It became more organized. It became more structured. And as structure emerged, as pebbles became the dominant population in many regions, a new threshold approached, the threshold where gravity could finally take over. The first stage of planetary building was underway, but it was only the beginning. There would be many more stages, many more transformations, many more phases where the scale would increase and the violence would intensify. The next stage would see pebbles accumulate into planetesimals, kilometre-scale objects, objects massive enough that gravity began to dominate, objects large enough that they could not be easily destroyed by collisions. The solar system was stepping up. It was scaling up. From dust to pebbles to planetesimals would be the next transformation. And from there to protoplanets. And from protoplanets to planets. The process was underway. The machinery was in motion. Nothing could stop it now. These pebbles participated in collective processes that eventually formed kilometre-scale planetesimals. This is where the narrative accelerates. Pebbles were no longer too small for gravity to matter. Kilometre-scale objects, planetesimals, these were large enough that gravity, though still relatively weak compared to chemical bonding, began to play a role. Planetesimals were bodies tens to hundreds of miles across. Some were a few miles. Some were hundreds of miles. Genuine objects, substantial enough to possess significant mass and generate measurable gravitational fields. When planetesimals encountered each other, gravity began to matter. Their gravitational fields, though individually tiny, became relevant. Planetesimals could attract each other across distances. They could pull at each other. And when they collided not as separate objects that bounced apart, but as unified bodies that merged. Once planetesimals formed, gravity became the dominant force. Self-gravity took over from drag and collision as the primary mechanism of growth. The era of gentle accumulation ended. The era of violent merger began. Planetesimals began attracting each other gravitationally. Imagine thousands of planetesimals in a region of space, all pulling at each other through gravity. Imagine them spiraling inward, their orbits decaying, collisions becoming inevitable. When planetesimals collided, they did not bounce apart. They merged completely. The collision released enormous amounts of energy. Materials melted. The two bodies became one. Each collision made the surviving body larger and more massive. Each increase in mass increased the gravitational force of that body. A larger body attracts material more strongly than a smaller body. A more massive body has a stronger gravitational field, which attracted more material, which led to more collisions, which increased mass further. This is runaway growth. This feedback cycle. It is called runaway because it accelerates. Early collisions happened between bodies of similar size growing slowly. Planetesimals grew slowly, one merger at a time. But as they grew larger and more massive, their gravitational influence expanded dramatically. They attracted material from larger distances. Bodies that would not have collided before could now be pulled together by a more massive planetesimal. Collisions happened faster. Growth accelerated exponentially. What starts as a slow process becomes a rapid transformation. This exponential phase is crucial to understanding planetary formation. The early solar system was a much more violent place than our modern understanding usually captures. Collisions were not rare events happening occasionally in isolated regions. Collisions were normal. They were constant. They were ubiquitous. They were part of the building process itself. You did not form a planetesimal through a gentle, orderly process. Every planetesimal that formed did so through countless impacts. Every merger was an explosion of energy. Temperatures soared at impact sites, materials melted, vaporized, recondensed. The disk was not just forming planets, it was cooking them, heating them, transforming them through violence. The The scale of these collisions is almost incomprehensible to modern minds. Modern explosions, thermonuclear weapons, the most violent events humanity has ever created. These would be whispers compared to what regularly occurred in the early solar system. Impacts with energy millions of times greater than any explosion ever created by humanity were everyday occurrences in this primordial solar nebula. Planetesimals crashed into each other at velocities that defy comfortable description. Miles per second, tens of miles per second. The kinetic energy of a collision between 2-kilometer-scale planetesimals traveling at such speeds is beyond reasonable calculation. It is beyond what we normally think about when we imagine collisions. The protoplanetary disk was not a peaceful place of gentle accretion. It was a cosmic war zone where gravity played referee and violence was the only rule. Every object in the disk was engaged in a cosmic competition. Every planetesimal was trying to consume its neighbors. Every collision was a conquest. Every merger was a victory for the winning body and a total defeat for the absorbed one. This was not conscious competition. These were not living organisms with strategies and intentions. But the dynamics were exactly as if they were. The successful planetesimals grew larger. The unsuccessful ones were consumed and ceased to exist as independent entities. Natural selection operated on the planetesimal population, just as it operates on biological populations. The strong survived. The large grew larger. The small were absorbed. And the violence was about to get worse. The next phase would transform the solar system in ways that would reshape it fundamentally. The next phase would involve not just planetesimals, but protoplanets. Not just growing bodies, but worlds. And the collisions would reach scales that defy reasonable description. And gravity, once it started pulling these objects together, did not stop. Once runaway growth began, it became unstoppable. Kilometer-sized planetesimals continued to merge. They collided repeatedly. Thousands of collisions. Millions of collisions. Gravity grew stronger with each coalescence. The process accelerated beyond the runaway phase into something else entirely. Protoplanets emerged. These were Mars-sized bodies, massive enough to clear their orbital zones by absorbing or ejecting smaller objects. Protoplanets numbered in the hundreds at first, though that number would decline through continued collision and gravitational interactions. Between 100 and 1,000 protoplanets, scattered throughout the solar system. Each one a world unto itself. Each one still growing. Each protoplanet was itself a world of tremendous energy, heated from the inside by radioactive decay of short-lived elements like aluminum-26, and from the outside by constant bombardment from infalling material. The early solar system at this stage contained several hundred planetary embryos, with masses comparable to Ceres or Pluto, though at this time these bodies were actively growing rather than dormant and stable. They were alive with energy. They were transforming rapidly. The collisions that created these embryos were catastrophic in the truest sense. They released unimaginable quantities of energy, more energy than we can reasonably comprehend. This energy melted the interiors of growing worlds. Parts of protoplanets experienced conditions so extreme that material vaporized. Rock turned to gas, metal vaporized. The surface of a young protoplanet could be hundreds of degrees Celsius. The interior could be thousands of degrees, incandescent, molten, barely distinguishable from plasma. Inside these melted zones, a critical process occurred called planetary differentiation. This process is absolutely central to understanding why planets have the structure they do today. Heavier elements, primarily iron and nickel, sank toward the center. They sank not through any active mechanism, but simply through gravity and density. Denser materials are heavier. They sink. Lighter elements, primarily silicate rocks, rose toward the surface. They floated upward through the molten interior. This separation happened passively, as denser materials simply sank under gravity, while less dense materials floated upward. The result was the layered structure we see in planets today. Dense iron cores surrounded by rocky mantles and lighter crustal layers. Earth has this structure. Mars has this structure. Every terrestrial planet has this structure because everyone experienced this violent, molten, differentiated phase. Without this violent collisional process, without the extreme heat and pressure generated by constant impacts, planets would have remained undifferentiated clumps of primordial material. Everything mixed together, no structure, no organization. Iron and silicate would remain separated by accident, not by process. Instead, the violence itself created structure. The chaos itself created order. Planetary differentiation was not an accident. It was an inevitable consequence of the extreme violence of planetary formation. Violence created the architecture of worlds. It is a paradox. Chaos created order. Destruction created structure. Every layer in Earth's interior, every zone in its composition, every aspect of its structure traces back to these ancient collisions, to this ancient violence, to this ancient chaos that organized itself through the relentless action of physics and gravity and impact. And the transformation was far from complete. The early solar system at this stage was alive with energy and motion. Protoplanets orbited the Sun, but not in the stable, predictable orbits we see today. These orbits were chaotic. They intersected. They collided. They crossed each other's paths constantly. The young solar system was not organized. It was anarchic. It was wild. It was dangerous. It was dynamic. The protoplanets were themselves still growing, still being shaped by impact, still being reorganized by gravitational encounters. The solar system was still forming. It would not reach its current configuration for hundreds of millions of years. But the fundamental process was established. Gravity pulled. Collisions happened. Larger objects grew larger. The system accelerated its own transformation. The snowball was rolling. It was gathering mass with every rotation. It was accelerating down the cosmic hill, gathering momentum, building speed. And nothing could stop it now. The solar system was committed to planetary formation. The process of creating worlds had begun, and it would not conclude until the solar system had been fundamentally restructured, reorganized, and stabilized into the form we recognize today. This was only the beginning. The chaos was far from complete. The violence had barely started. The true catastrophes were still to come, and the greatest catastrophes of all were yet to unfold. The snowball was rolling. It was gathering mass with every rotation. It was accelerating down the cosmic hill, gathering momentum, building speed, and nothing could stop it now. The solar system was committed to planetary formation. The process of creating worlds had begun, and it would not conclude until the solar system had been fundamentally restructured, reorganized, and stabilized into the form we recognize today. But this was only the beginning. The chaos was far from complete. The violence had barely started. The true catastrophes were still to come. And the greatest catastrophes of all were yet to unfold. Here is where the transformation accelerated beyond anything that had come before. By the time several hundred protoplanets had formed scattered across the inner and middle regions of the early solar system, something else happened. Something that makes the pebble to planetesimal violence look almost quaint by comparison. The gravitational interactions between these massive bodies began to destabilize the entire system. This destabilization was not random chaos, though it appeared that way. It was physics, pure, inexorable physics, working at scales almost beyond human comprehension. Protoplanets did not orbit in perfect, predictable circles around the Sun. They orbited in slightly elliptical paths. These ellipses were not concentric. They were not aligned. They intersected each other. They crossed through the same regions of space. When orbits cross, collisions follow. It is not a matter of if, but when. The early solar system at this stage contained hundreds of protoplanetary bodies, some as large as Mars, all orbiting, all moving, all following gravitational dictates, all on paths that would eventually bring them into contact with other massive bodies. Occasionally, when two protoplanets approached each other more closely than usual, their gravitational fields began to interact significantly. Gravity operates over a distance, but its effects grow stronger as distance decreases. The strength of gravity follows the inverse square law. Double the distance, and gravity becomes 1/4 as strong. Halve the distance, and gravity becomes 4 times as strong. When two massive objects come near each other, their gravitational forces become the dominant force controlling both their dynamics. When gravity from one protoplanet affected another, it changed the other's orbit. It did not do this gently or slowly. The orbit shifted. Suddenly, dramatically. The protoplanet that was struck by the gravitational influence found itself on a new path, a new trajectory determined by the gravitational pull of its neighbour. Perhaps this new path would bring it into collision with another body. Perhaps this new path would lead it away from danger for the moment. But the change was immediate and real. These small changes accumulated. When one protoplanet's gravity perturbed another, that perturbed protoplanet now moved on a new path. And because it was on a new path, it could interact with different protoplanets. Its gravitational field could now perturb bodies it might never have encountered on its original trajectory. This created a cascading effect. Gravitational perturbations begat more gravitational perturbations. Orbits became more chaotic. Ellipses grew more extreme. Some protoplanets found themselves on trajectories that took them far from other bodies. These were the lucky ones, though luck is a meaningless concept in orbital mechanics. Some protoplanets found themselves on trajectories that brought them into contact with other massive bodies. These collisions became inevitable. The early solar system was not organized like ours is today. It was anarchic, chaotic, unpredictable. Protoplanets careened through space on intersecting paths, their trajectories determined by countless gravitational interactions, each one sending them in slightly different directions, each one bringing some closer to collision and others farther away. Some protoplanets passed close to each other without colliding, missing by thousands of kilometers, which in solar system terms is a near miss, but still separation. Some collided directly with catastrophic consequences. When protoplanets collided, something remarkable and destructive happened simultaneously. They did not bounce apart like two billiard balls deflecting off each other at angles determined by geometry and momentum. They were not elastic objects. They were not hard spheres. They were massive objects made of rock and metal and ice, held together by their own gravity and internal pressures. When two such objects collided at velocities of tens of kilometers per second, something fundamentally different happened from ordinary collisions. They merged. Completely, catastrophically. They fused into a single body. The merger was total. Neither of the original protoplanets existed anymore. One protoplanet striking another meant the end of both as independent entities. Instead, there was a new protoplanet, a larger one, a more massive one. All the mass of both objects was now combined. All the material of both bodies was now part of a single gravitational system. All the iron and silicate and water ice and lighter elements that had existed as two separate objects now existed as one unified mass. A collision between two protoplanets was the most violent event imaginable, short of stellar explosion or supernova. The kinetic energy released by such a collision defies reasonable calculation. Try to imagine it. A Mars-sized protoplanet traveling at tens of kilometers per second, striking another Mars-sized protoplanet traveling in a different direction at tens of kilometers per second. The energy in such a collision is astronomical in both the literal and mathematical sense. It is millions of times greater than any explosion humanity has ever created. More energy than the entire nuclear arsenal of every nation on Earth multiplied together and detonated simultaneously. More energy than any natural disaster that we consider apocalyptic. More energy than earthquakes and tsunamis and hurricanes combined. And it was released in an instant, not gradually over hours or days, in a single impact that lasted mere seconds. The collision vaporized vast quantities of material. Rock does not simply crack or break when struck at such velocities. It vaporizes. The material becomes gas. It transforms into a completely different state of matter. The impact site itself turned to plasma, that extreme state where atoms are stripped of their electrons and exist as pure energy and charged particles. Temperatures at the impact site soared into the thousands of degrees Celsius. Pressures reached extremes that would seem like pure science fiction if they were not verified by astronomical observation and computer simulation and the evidence preserved in meteorites and lunar samples brought back by astronauts. The result of such a collision was a newly formed, larger protoplanet, much hotter than either parent body, more massive than either predecessor, more gravitationally dominant in its region of space, more influential over other bodies orbiting nearby. This process, violent as it was, repeated continuously throughout the early solar system. Not just once or twice or a dozen times, hundreds of times, thousands of times, tens of thousands of collisions over tens of millions of years. Protoplanets collided and merged. The largest protoplanets grew larger through accumulating material from smaller bodies. Smaller protoplanets were absorbed into larger ones and ceased to exist as independent entities. This was not selection in any biological sense, though the dynamics were remarkably similar to natural selection in evolutionary systems. This was purely gravitational, pure physics, pure mathematics. Larger masses attracted smaller masses more strongly through the inverse square law of gravity. Larger bodies could survive collisions that would destroy smaller ones because they had more mass, more gravitational binding energy, more structural integrity. The largest bodies grew larger still. The smallest bodies disappeared into larger ones. Natural selection operated on the protoplanet population through gravity and collision and the relentless action of physics operating at planetary scales. It was survival of the largest and most massive. This process is known as runaway growth because once it starts, it accelerates exponentially. Early collisions happened between bodies of similar size, growing the population slowly. But as the largest bodies grew larger and more massive, their gravitational influence expanded dramatically. They attracted material from larger distances. Bodies that would not have collided before could now be led together by a more massive protoplanet. Collisions happened faster. Growth accelerated exponentially. What starts as a slow process becomes a rapid transformation. What was growing at a certain rate becomes growing much faster. Each new merger creates a more massive body. Each more massive body attracts more material. Each attraction creates more collisions. The system feeds back on itself. This exponential phase is crucial to understanding planetary formation. Without runaway growth, planets would not form in reasonable timescales. The universe would be a different place. With runaway growth, they could form in tens of millions of years. The protoplanetary disk was organized by this violence into distinct zones. Different regions had different collision rates. Different regions had different densities of material. The inner solar system, closer to the Sun, where temperatures soared above the melting points of most volatile compounds, became dominated by rock and metal. The outer solar system, far from the sun where temperatures plummeted well below the freezing points of water and methane and ammonia, remained a realm of ice and frozen gas. This temperature gradient had been established when the sun ignited. It had been reinforced continuously by the sun's ongoing radiation and heat. The solar wind, the stream of charged particles flowing outward from the young sun's surface, helped to further deplete the inner solar system of volatile materials. Lighter elements were blown outward toward the colder regions. Denser materials remained closer to the sun. The result was that the inner solar system became the domain of terrestrial planets. Small, dense, rocky, Earth, Mars, Venus, Mercury. These planets would form in the inner solar system through the collision and merger of protoplanets made of rock and metal. The outer solar system would become the domain of gas giants, massive bodies capable of capturing hydrogen and helium directly from the nebula. Jupiter, Saturn, Uranus, Neptune. These would form through different processes and reach different sizes. But for now, in T, his era, the focus was on the inner solar system, the era of terrestrial planet formation. And the era of violence was reaching its crescendo. The violent phase of terrestrial planet formation lasted tens of millions of years. Some estimates place it at 50 million years. Some place it longer, perhaps 100 million years or more. The exact timeline is uncertain because the evidence has been destroyed or buried deep within planets where it can no longer be directly observed by astronomers. But the scale was consistent across all estimates, tens of millions of years. In the context of human history, this seems like forever. We cannot even conceive of 50 million years properly. Homo sapiens has existed for only about 300,000 years. 50 million years is more than 150 times the entire existence of our species. Homo sapiens has been around for less than 1% of this timescale, and yet in cosmic terms, the violent phase was brief, a blink, a moment, a flash. But in that moment, the solar system was transformed completely. The dozens or hundreds of protoplanets that filled the inner solar system at the peak of the violent phase were reduced through collision and merger to just a handful. Mercury, Venus, Earth, and Mars, 4 terrestrial planets. This reduction happened not through some orderly process designed by any intelligence, but through chaos and random gravitational interactions and the relentless action of physics. Protoplanets that collided head-on were destroyed or completely merged together. Protoplanets that were struck by glancing blows were sent careening into new orbits where they collided with other protoplanets. Gravitational interactions between bodies that did not collide directly still altered the higher orbits, making them vulnerable to impacts with other massive bodies. The solar system at this stage was in constant flux. Bodies were moving. Orbits were changing continuously. Collisions were happening regularly. New configurations were emerging constantly. Stable orbits did not exist. Order had not yet emerged. And through all of this chaos, through all of this violence, the 4 terrestrial planets we know today were gradually assembled from countless protoplanetary collisions. Each collision added material. Each collision added energy. Each collision shaped the world that emerged. Though each collision released enormous amounts of energy, this energy went somewhere. Mostly it went into heat. The interiors of growing planets were melted by the constant bombardment. A rock that melts gives off or absorbs energy depending on which direction the transformation goes. But rock that vaporizes and then recondenses releases tremendous heat. The growing planets experienced repeated melting and remelting by the constant onslaught of impacts. Their interiors became extremely hot, but some of the energy from collisions went into spin. Some collisions struck protoplanets at an angle. These glancing blows imparted angular momentum. They caused protoplanets to spin faster. A direct impact along the axis of rotation would have less effect on spin. A glancing impact perpendicular to the axe could cause significant increase in rotation rate. By the end of the violent phase, the terrestrial planets were spinning. They had angular momentum. They had rotation. This rotation was a legacy of the violent collisions that formed them. Earth today spins with a rotation period of 24 hours. This was determined not by some orderly process, but by the chaotic sum of countless collisions in the violent era. The orientation of Earth's rotation axis is what we call the axial tilt. It is tilted relative to the plane of Earth's orbit around the Sun, at an angle of about 23.5 degrees. This tilt is what gives us seasons. It is why summer brings longer days and higher sun angles and more intense heat. It is why winter brings shorter days and lower sun angles and less intense heat. Without this tilt, Earth would not have seasons in the form we experience them. It would have relatively uniform climate throughout the year across most regions. This tilt was also imparted during the violent era. It was not designed. It was not optimized for anything. It was simply the consequence of the specific sequence of collisions that created Earth. Many scientists believe that one particular collision was responsible for much of this tilt. A single impact so massive and so important that it deserves its own detailed discussion. This impact was so significant that it may have not only tilted Earth, but also created the Moon. Among all the collisions that occurred during the violent era of terrestrial planet formation, one stands out as uniquely catastrophic. This collision involved Earth and another protoplanet that existed in the early solar system alongside the hundreds of other bodies that were still coalescing into planets. This other protoplanet was Mars-sized, perhaps 10% of Earth's mass, perhaps slightly larger, perhaps slightly smaller. The exact size is unknown because the body has long since ceased to exist as an independent entity. It has been completely incorporated into Earth or scattered across the solar system. But it was substantial, large enough to be a significant protoplanet in its own right, large enough to have its own gravitational field capable of affecting other bodies, large enough to cause immense destruction when it collided with Earth. Scientists have named this protoplanet Theia, after a name from Greek mythology. In Greek mythology, Theia is the mother of Selene, the goddess of the moon. The name is poetic. It is also accurate and fitting, because this collision, the collision between Earth and Theia, is believed to be the event that created the moon. This is now called the giant impact hypothesis, and it has become the leading explanation for how the moon formed. The collision likely occurred about 4.4 to 4.45 billion years ago. This is 50 to 100 million years after the solar system began to form, early in Earth's history. When Earth was still mostly molten from its violent assembly out of dozens of protoplanetary bodies. When Earth was still assembling itself from protoplanetary material and had not yet reached full stability. When Earth was still young and violent and unstable, the system was still chaotic. Orbits were still crossing. Collisions were still happening regularly. Theia approached Earth gradually, pulled inward by gravitational interactions with other bodies and the overall dynamics of the chaotic early solar system. The two bodies were in orbit around the Sun. Their orbits intersected or came very close to intersecting. Or perhaps they collided by chance through gravitational interaction with a third body that deflected one or both of them onto a collision course. The exact mechanics of how they came together are still debated by planetary scientists. But eventually, they collided. The collision was not head-on, not a direct impact along the line connecting their centers of mass. It was oblique. Theia struck Earth at an angle, not directly perpendicular to Earth's surface, but at a glancing angle, perhaps something like a 45-degree angle, or perhaps even steeper and more grazing. This matters profoundly because the angle of impact determines the outcome. A head-on collision might have destroyed both bodies completely, sent their material scattering across the solar system, preventing the formation of either body as a unified world. An oblique collision was more constructive, more creative in its destruction. It preserved material. It reorganized it. It transformed it. It had the potential to create something new from the destruction. When Theia struck Earth, the impact was catastrophic beyond any reasonable description. Imagine an object the size of Mars, traveling at tens of kilometers per second through the void of space. Imagine the speed. Not like an airplane moving at a few hundred kilometers per hour. Not like a rocket moving at kilometers per second. Faster than almost anything humans have ever created. Tens of kilometers per second. Some estimates suggest 4 kilometers per second as a minimum. Some suggest much faster. Maybe 10 kilometers per second or more. Imagine this Mars-sized object with all its mass and all its momentum, striking a nearly Earth-sized object moving in a different direction at a different velocity. The kinetic energy of such a collision is incomprehensible by human standards. More energy than the nuclear arsenal of every nation on Earth multiplied by millions. More energy than any event in recorded human history. More energy than all the natural disasters we consider apocalyptic combined. More energy than earthquakes and tsunamis and hurricanes and tornadoes all combined and multiplied by millions. And it was released in an instant. In a single impact that lasted mere seconds, the collision vaporized vast quantities of material. Rock does not simply shatter at such energies. It does not crack or break into fragments. It vaporizes. It transforms into gas. The impact site itself turned to plasma, that extreme state of matter where atoms are stripped of their electrons and exist as pure energy and charged particles. Temperatures at the impact site soared to tens of thousands of degrees. The explosion was so tremendous that material was ejected outward in all directions. Not just a little material, not just some fragments. Vast quantities of rock and gas were thrown into space. This ejector, this expelled material, followed different trajectories depending on the energy imparted and the angle of ejection. Some material escaped Earth's gravity completely and was lost to space or captured by the sun. Some of it remained in orbit around Earth. It was too fast to fall back down to the surface, but too slow to escape Earth's gravitational influence completely. This orbiting material began to interact gravitationally. It coalesced, it merged, it accumulated. And from this accumulated material, the Moon was born. The exact process of lunar formation from the impact ejector is still debated by lunar scientists and planetary formation experts and researchers who study the Moon's origin. Some scientists propose a gradual process where the ejector slowly accumulated over thousands or millions of years into a coherent body. Others propose a more rapid process where the Moon formed almost immediately, perhaps within hours of the impact, coalescing rapidly from the material in orbit. Computer simulations suggest that the Moon could have formed very quickly, even within a single rotation period of the early Earth. The computational results point toward a relatively rapid assembly from the impact debris. The newly formed Moon would have orbited very close to Earth, much closer than it orbits today. How close? Some estimates suggest just a few thousand kilometers away from Earth's center. Earth at that time was spinning rapidly, perhaps with a rotation period of just a few hours, maybe only 3 or 4 hours per full rotation. The Moon, formed in near-Earth orbit so close to Earth, would have been subject to tremendous tidal forces. Tidal forces from Earth would have acted on the Moon, distorting it and affecting its orbital dynamics. Tidal forces from the Moon would have acted on Earth, distorting the planet itself and causing friction and heat generation. These tidal forces would have caused the Moon to gradually spiral outward, and they would have caused Earth's rotation to gradually slow. This process continues today, though very slowly and much less dramatically than in the early solar system. The Moon is still spiraling outward at about 4 centimeters per year. Earth's rotation is still slowing at about 1.7 milliseconds per century. But the effect was much more dramatic in the early solar system, when the Moon was much closer and the tidal forces were much stronger. When the Moon was just thousands of kilometers away, tidal forces were thousands of times stronger. When the Moon was 100 times closer, tidal forces were 1,000,000 times stronger. Over millions of years, the Moon spiraled outward to larger and larger orbits. As it did, it carried angular momentum away from Earth. This caused Earth's rotation to slow. The Moon's orbital motion represented rotational energy that was no longer in Earth's spin. The rate of Earth's rotation decreased. The length of an Earth day increased from a few hours to many more hours. This process would have taken a very long time by human standards. But in cosmic terms, it was relatively quick. Perhaps a few 100,000 years for the Moon to reach an orbit of reasonable stability. Perhaps 1,000,000 years or more. The exact timeline is uncertain. But by several million years after the impact, the Moon had reached something close to its modern orbital distance of about 384,000 kilometers. The impact with Theia left permanent marks on Earth. It tilted Earth's rotation axis. It gave Earth a rapid rotation. It imparted enormous amounts of energy to Earth's interior. The impact melted Earth extensively. Already molten from its violent formation from dozens of protoplanetary collisions, Earth became even more molten. The entire surface would have become an ocean of lava. The impact also stripped away part of Earth's primordial atmosphere. But it did not destroy Earth. Earth survived. Earth continued to exist. Earth continued to orbit the Sun. And Earth now had a companion, the Moon. A new body in Earth's orbit. A new gravitational presence in the solar system. The Moon formed not through some gentle accretion process, but through apocalyptic collision, and the Moon carried the signature of this violent origin in every one of its properties. The Moon's composition is unusual and distinctive. It lacks volatile materials like water and oxygen and light elements that are abundant in meteorites from asteroids. This is consistent with a formation from impact ejecta that was vaporized and recondensed. The energy released by the impact would have vaporized these volatile materials. They would have been lost to space or remained in the gas phase and dissipated into the early solar system. Only the less volatile, higher melting point materials would have remained in orbit to form the Moon. This is why the Moon is so dry, so lacking in water compared to Earth. The Moon's isotope ratios are nearly identical to Earth's, and this is strong evidence that the Moon formed from material that came from Earth and from Theia. Isotopes are differ, nth forms of the same element with different numbers of neutrons. Different locations in the solar system have different ratios of isotopes. If the Moon had formed elsewhere in the solar system and been captured by Earth through gravitational interaction, it would have different isotope ratios from Earth. Different meteorite parent bodies have dramatically different isotope ratios. But the Moon's isotope ratios are nearly indistinguishable from Earth's when measured in laboratories. This is consistent with a formation from impact ejecta, where material from both Earth and Theia mix together. The Moon is also unusually large relative to Earth. Other planets have moons, but Earth's moon is exceptional. It is about 1/4 the diameter of Earth. This is a very large moon. Most planets have much smaller moons proportionally. Mercury and Venus have no moons at all. Mars has 2 tiny moons named Phobos and Deimos, each only a few kilometers across. Jupiter has many moons, dozens of them, but none as proportionally large as Earth's moon. This unusual size is also explained by the giant impact hypothesis. An impact large enough to form the Moon would naturally create a very large satellite because the impact would eject a tremendous amount of material. A smaller impact would have ejected less material and formed a smaller moon or no moon at all. The collision with Theia was the most significant event in Earth's early history. It shaped Earth's fundamental properties. It determined Earth's rotation. It determined Earth's axial tilt. It created the Moon. It shaped Earth's early climate by affecting the planet's rotation rate. It affected Earth's magnetic field generation by altering the dynamics of Earth's molten interior. Virtually every major feature of Earth today can trace its origin back to this single collision. And yet, it was one of thousands of collisions, one of countless events that shaped the early solar system. This collision was notable because it was massive, because it created the Moon, because it shaped the planet that would eventually harbour life. But it was not unique in character. Many other collisions occurred. Many other protoplanets were destroyed. The Earth that emerged from the violent era was not the product of a single collision, but of countless collisions. Third, the Moon was the product of one particular collision, but Earth itself was constructed through a violent process that involved the merger of dozens of protoplanetary bodies over tens of millions of years. Each collision added to Earth's mass. Each collision added to Earth's heat. Each collision added to Earth's angular momentum. The cumulative effect of all these collisions was the creation of the planet we know today. By the time the violent phase of terrestrial planet formation ended, roughly 50 to 100 million years after the solar system formed, Earth had assembled itself into roughly its current size and structure. Earth was fully formed. Earth had acquired a moon. Earth had its rotation and its axial tilt determined by a Mars-sized collision. Earth had differentiated into a dense iron core, a rocky mantle, and a thin crust. Earth was ready for the next phase of its evolution. The next phase would not be the formation of the planet itself, but the modification of the planet through continued bombardment and the emergence of oceans and atmospheres. Water would condense from the atmosphere and form oceans. Volcanic outgassing would thicken the atmosphere with carbon dioxide and nitrogen. Eventually, life would begin to emerge. But before that next phase could even begin, before Earth could settle into relative stability, the solar system as a whole had to undergo another transformation, one that would be even more violent than what had come before, one that would threaten everything that had formed in the inner solar system. The outer planets, Jupiter and Saturn and Uranus and Neptune, had been forming in their distant orbits, while the inner solar system experienced its violent phase. They had assembled themselves through different processes, capturing gas and ice and forming as massive giants. But their orbits were not stable. They were affected by the countless planetesimals and remnants of planet formation that orbited between them and around them. The gravitational interactions with these planetesimals were slowly changing the orbits of the gas giants. Over millions of years, the outer planets had been migrating. They had been moving. Their orbits had been changing. And these changes were about to reach a critical point. The outer planets were about to move dramatically. They were about to migrate violently across the solar system. And when they did, they would trigger a cataclysm that would reshape the entire inner solar system once again. The largest bombardment period in Earth's history was about to begin, and the violence was far from over. The migration had begun. About 4 billion years ago, roughly 500 million years after the solar system formed, something shifted fundamentally in the orbits of the giant planets. Jupiter and Saturn, moving in their distant orbits far beyond the region where Earth and Venus and Mars orbited, began to interact more directly with the countless planetesimals that surrounded them. These interactions were not gentle. Gravity is never gentle when operating at such scales. A planetesimal approaching Jupiter found its trajectory altered dramatically. Its velocity changed. Its orbit bent. Some planetesimals were scattered inward, sent careening toward the inner solar system, where Earth waited. Others were scattered outward. Some were ejected from the solar system entirely. But the cumulative effect of millions of these interactions was slow, inexorable, and catastrophic. Jupiter and Saturn began to migrate. Their orbits changed. They moved. slowly at first, then faster as the migrations accelerated and fed back on themselves. Imagine the situation. Jupiter, already enormous by any standard, with a mass more than 300 times greater than Earth, was exerting tremendous gravitational influence across a vast region of space. When planetesimals fell toward Jupiter, gravity accelerated them to speeds of tens of kilometers per second. The closer a planetesimal got to Jupiter, the stronger the gravitational pull became, and the faster it moved. If a planetesimal came close enough to Jupiter, but not close enough to be captured entirely, Jupiter's gravity would bend its trajectory, changing its velocity and direction without destroying it. The planetesimal would be flung away at a different angle, on a different orbit than it had before. This process, called gravitational scattering, happened constantly. Millions of times, perhaps billions of times. Each scattering event was a small perturbation, but add them together, accumulate them over millions of years, and the effects become significant. The combined gravitational scattering of billions of planetesimals gradually altered Jupiter's orbit. Jupiter moved inward. It migrated toward the Sun. And as Jupiter moved, it interacted with more planetesimals on new orbits. Saturn, farther out, was affected by Jupiter's presence more strongly as Jupiter moved closer. Saturn began to migrate as well. This process, known as planetary migration, is one of the most significant events in solar system history because it reorganized everything. The outer planets did not maintain their original orbits. They could not. The gravitational interactions with the planetesimal disk destabilized them. Jupiter moved inward first, pulled toward the Sun by gravitational interactions with the planetesimals. But then something remarkable happened. Jupiter reached a point where it interacted with Saturn. The two giant planets fell into a resonance, a gravitational lock where Saturn orbited the Sun once for every 2 orbits that Jupiter completed. This 2-to-1 resonance created a gravitational push against the outer planets. Uranus and Neptune, which had formed farther out in the solar system, found themselves suddenly pushed by this gravitational wave emanating from Jupiter and Saturn. They were knocked outward. Their orbits expanded dramatically. Uranus and Neptune were scattered onto much larger orbits than they originally occupied. The Grand Tack model, developed by planetary scientists to explain these dynamics, suggests that Jupiter not only moved inward, but reached a point in its migration called the tack, where it achieved a position closer to the Sun than it would eventually occupy. At about 1.5 astronomical units from the Sun, Jupiter was relatively close, much closer than its current orbital position of 5.2 astronomical units. This inward migration of Jupiter was catastrophic for the asteroid belt and for the regions where Mars was forming. As Jupiter moved inward, its gravity disrupted everything in its path. Objects that were coalescing to form Mars were scattered. Material that could have become part of Mars was ejected. The growing proto-Mars never reached the size that Earth achieved because Jupiter's inward migration depleted the material available to proto-Mars. This is why Mars is only about 11% of Earth's mass, much smaller than we might expect if the terrestrial planets had formed under more uniform conditions. Then Jupiter was pulled back outward again, moving back to positions farther from the Sun. This outward migration was driven by its interaction with Saturn and the remaining planetesimals. Jupiter moved back out past its current position, then gradually settled into the orbit we see today. The entire process, the inward tack and the outward migration, happened over a period of a few million years, but the consequences persisted for hundreds of millions of years. This is where the catastrophe began for the inner solar system. As the outer planets migrated and were scattered, as Jupiter moved inward and then outward again in what scientists call the Grand Tack, the planetesimal disk that surrounded the solar system was destabilized completely. Objects that had been in relatively stable orbits for hundreds of millions of years were suddenly on unstable paths. Billions of planetesimals, comets, and asteroids found their trajectories altered by the new gravitational configuration. Many were scattered outward, but many were scattered inward, toward the inner solar system, toward Earth, toward Mars, toward Venus, toward Mercury. This inward scattering was not a gentle rain of material. It was a bombardment, a cosmic assault, an unprecedented onslaught of impacts that would reshape the inner planets and leave scars that persist to this day. The late heavy bombardment, as scientists now call this period, lasted between 20 and 200 million years, depending on the models and the data. It began around 4.1 billion years ago and continued until approximately 3.8 billion years ago. During this entire period, the impact rate on the inner planets was perhaps 100 times greater than what we see today. Every day brought massive impacts. Every week brought global catastrophes. Every month brought extinction-level events. The bombardment was relentless. It was sustained. It was utterly destructive in its implications. Think about what that means. Right now, in our modern solar system, the inner planets are struck by relatively few large impactors. There was the impact 66 million years ago that killed the dinosaurs, yes, but that was an exceptional event, something that happens only once every tens of millions of years or more. During the late heavy bombardment, impacts of that scale or larger were happening multiple times per million years. The background impact rate was unimaginably high. The Moon, closest to Earth and protected to some degree by Earth's gravitational influence but also more exposed to impacts from different angles, was pummeled repeatedly. Large basins were carved into the lunar surface by kilometre-sized impactors. The Imbrium Basin, one of the largest impact structures on the Moon, was created during this period about 3.85 to 3.9 billion years ago by an impact so massive that it flooded with lava afterward. The basin is 1,150 kilometers across. Imagine a single object traveling at tens of kilometers per second, striking the Moon with enough force to excavate a crater larger than France. Imagine hundreds of such impacts, thousands of them, all happening within a span of a few 100 million years. The lunar surface was being constantly resurfaced by impactors. Craters formed and were immediately overwritten by newer craters. Lava flowed from the heat of impacts, only to be covered by subsequent impacts. The Moon was literally being remade by the bombardment. Evidence for the late heavy bombardment comes from multiple sources, but the most direct evidence comes from the Moon itself. When Apollo astronauts visited the Moon in the 1960s and 1970s, they brought back rocks. More than 380 kilograms of lunar samples were collected across multiple missions, providing an unprecedented window into the Moon's ancient history. These rocks contain something called impact melt, a type of rock that only forms when material is heated instantly to such extreme temperatures that it melts upon being struck by an impactor traveling at cosmic velocities. Normal rock melts at temperatures around 1,000 to 1,500 degrees Celsius, depending on the composition. But an impact melt, created by the compression and instantaneous heating of an impact, requires extreme energies that transform rock into liquid in milliseconds. Scientists studied these rocks carefully, examining them under microscopes, analyzing their chemical composition, determining what elements they contained and in what proportions. They dated them using radiometric methods, measuring the decay of radioactive isotopes to determine how long ago the rocks had last been molten. The method is remarkably precise. Potassium decays to argon at a known rate. Uranium decays to lead. By measuring the ratio of parent isotope to daughter isotope in a rock, scientists can calculate exactly how much time has passed since the rock last crystallized from a molten state. The results were striking. Many of the samples, despite coming from different locations on the near side of the Moon, all dated to roughly the same time period, around 4 billion years ago. Some samples clustered even more precisely around 3.9 billion years. This clustering of impact ages was not random. It was not coincidence. It was evidence of an actual event, a real bombardment, a genuine period when impacts were concentrated in time and space. The sample from the Imbrium Basin region showed evidence of being melted in an impact 3.85 to 3.9 billion years ago. Other samples from other locations showed similar ages, with very few samples showing older impacts. This pattern suggested that impacts were common around 4 billion years ago and much less common before that. Something changed. The change was the migration of the giant planets. The change was planetary migration, triggering the late heavy bombardment. The NICE model, named after the French city where the theory was developed, provides the most comprehensive explanation for this sequence of events. According to the NICE model, the giant planets started in a more compact configuration than they occupy today. They were closer together. Their orbits were more tightly packed. Jupiter was at perhaps 3.5 astronomical units from the Sun. Saturn was farther out, but still closer than its current position. Uranus and Neptune were even closer to the inner solar system than they are today, probably within the region where the asteroid belt resides. This initial configuration was stable for perhaps 500 million years, long enough for the terrestrial planets to form and solidify, long enough for the violent era of terrestrial planet assembly to wind down, and the 4 inner planets to reach something resembling their modern sizes. But then, through interactions with the remaining planetesimal disk, through gravitational interactions between the giant planets themselves, the orbits became unstable. The system entered a regime that astronomers call dynamical chaos. Small perturbations were magnified into large orbital changes. Jupiter migrated inward first, pulled toward the Sun by gravitational interactions with the planetesimals. Then a gravitational interaction with Saturn caused Jupiter to move back outward, while Saturn moved outward more rapidly. The 2 planets fell into and then out of resonance. Uranus and Neptune were scattered dramatically, moving from positions closer to the Sun to positions much farther out. Neptune moved far beyond the Kuiper belt, the region of icy bodies beyond Pluto, and actually may have moved temporarily even farther out before its orbit evolved to something close to its current position. Uranus moved outward as well, but not as far as Neptune, ending up between Jupiter and Neptune in the planetary lineup. This entire migration happened relatively rapidly once it began, perhaps over the course of a few million years, which is fast in astronomical terms, but the consequences lasted for hundreds of millions of years. As the outer planets migrated and were scattered, they ploughed through the planetesimal disk like massive objects moving through a cloud of smaller bodies. They collided with some planetesimals directly, transferring enormous amounts of energy and scattering the smaller bodies. They passed near others, their gravity bending and distorting the orbits of the smaller bodies without direct impact. The cumulative effect was to destabilize the entire disk. Objects that had been in stable, predictable orbits became unstable. Their orbital parameters changed. Their paths became more eccentric, more tilted. Many objects found themselves on trajectories that intersected the orbits of the terrestrial planets. Many objects found themselves on paths that led directly to the inner solar system. The asteroid belt itself was disrupted. The asteroid belt today contains relatively few objects, a sparse collection of rocky bodies orbiting in a wide region between Mars and Jupiter. But the asteroid belt in the early solar system was much more massive. It contained far more material. The NICE model suggests that most of this material was scattered. Some was scattered inward toward the terrestrial planets. Some was scattered outward, following the retreating giant planets into the outer solar system. The asteroid belt was largely emptied. What remains today is only a small fraction of the original belt. This emptying of the asteroid belt combined with the scattering of planetesimals from other regions of the young solar system, created a massive influx of material toward the inner planets. Not all of this material fell on Earth. Some fell on Venus, some fell on Mercury, some fell on Mars, some continued on new orbits in the solar system. But the inner planets, sitting directly in the pathway of this infalling material, experienced an unprecedented bombardment. The impact rate increased dramatically, persisting for tens of millions of years until the gravitational chaos gradually subsided and the outer planets settled into something close to their modern orbital configuration. Earth during this bombardment was no longer the relatively cool, newly formed world that had existed just hundreds of millions of years earlier. Earth had been impacted extensively during its own formation, melted by collisions, shaped by the Theia impact that created the Moon. But Earth had begun to cool. The surface had started to solidify. The earliest evidence suggests that by about 4.3 billion years ago, Earth's surface had cooled enough for water vapor in the atmosphere to condense on the surface and form oceans. Zircon crystals that scientists have analyzed show evidence of liquid water on Earth's surface at this time, providing the earliest direct evidence of oceans or liquid water on the young planet. But this was not a stable situation. The late heavy bombardment meant that Earth returned to a state of intense bombardment. Massive objects fell from space continuously. Each impact released energy on a scale that defies reasonable comprehension. An impact by a 100-kilometer object releases energy equivalent to millions of megatons of TNT. An impact by a 500-kilometer object releases billions of megatons. Each impact heated the atmosphere. Each impact vaporized material. Each impact sent dust and vaporized rock into the upper atmosphere, blocking sunlight and creating a global winter. The oceans that had begun to form were subjected to repeated shocks. Some impacts were large enough to boil oceans entirely, vaporizing them and sending the water high into the atmosphere where it would be lost to space or recondense over millions of years. What kind of life, if any, could exist on a world being pummeled by asteroids and comets with an impact rate 100 times greater than today? What kind of habitability could persist under such conditions? These are questions that scientists debate extensively because the late heavy bombardment occurred during a period when life may have already emerged on Earth, or may have been just about to emerge. Some scientists argue that the earliest evidence of life on Earth comes from around 3.8 billion years ago, which is when the bombardment was winding down. Other scientists argue that life emerged even earlier, perhaps 4.1 or 4.2 billion years ago, which would mean that life was emerging even as the bombardment was intensifying. If that is true, then life on Earth began its history being bombarded by asteroids and comets. The earliest life would have been subjected to extreme stress immediately after its emergence. The timing is crucial. The inner planets under siege during this period experienced vastly different fates. Mercury, the closest planet to the Sun, received tremendous numbers of impacts. Its surface, today, is covered with craters upon craters. Craters so numerous that ancient craters are obscured by younger impacts. The Mercurian surface resembles the lunar surface in many ways, a testament to an ancient, violent past. Mercury experienced the bombardment perhaps even more intensely than Earth or the Moon, because it orbited closer to the scattering centers of the inner solar system, where the planetesimals were most densely concentrated. Additionally, Mercury's small size meant that the proportional impact of bombardment was greater. Each impact represented a larger fraction of the planet's surface area. Large impacts on Mercury, measured as a fraction of the planet's total surface, were relatively more destructive than the same impacts would be on a larger body like Earth. Mercury today is a small, dense, heavily cratered world, and much of its character was determined by this intense early bombardment. Mars, the smaller terrestrial planet, also received countless impacts. But Mars was so small compared to Earth that the bombardment had more profound consequences. Mars is less than half the size of Earth by diameter, and only about 11% of Earth's mass. Each impact removed material from Mars's surface, heating it, vaporizing it, sending it into space. Mars lost atmosphere through these impacts. Each large impact would have stripped away part of the thin atmosphere that Mars was developing. The atmospheric escape from impacts on Mars was significant because Mars lacked the strong magnetic field and sufficient gravity to retain light elements like hydrogen and helium in its atmosphere. When an impact heated the upper atmosphere, the heat allowed gas molecules to escape into space at velocities greater than Mars's escape velocity. Over time, with impact after impact, Mars's atmosphere was depleted, reduced from something possibly similar to Earth's early atmosphere to the thin, tenuous thing we see today, less than 1% of Earth's atmospheric pressure. The bombardment contributed significantly to Mars's transformation from a potentially habitable world with liquid water and a thicker atmosphere to the cold, dry, barren desert we see today. Water that Mars had accumulated through impacts and through internal processes was frozen into ice caps and subsurface ice. Liquid water became rare. The relatively warm, wet Mars that may have existed in the earlier solar system was replaced by a cold, desiccated Mars. Venus received its share of impacts as well. Venus today is a hellish world, hot enough to melt lead, with an atmosphere so thick and toxic that no known life form could survive on its surface. The atmospheric pressure at Venus's surface is 92 times greater than Earth's atmospheric pressure. The temperature is hot enough to incinerate spacecraft designed to land on it. But Venus did not start out this way. Venus and Earth are similar in size. They likely formed through similar processes. Venus is only slightly smaller than Earth, and the two planets formed in the same region of the solar system, assembling from similar materials. In the early solar system, Venus may have been habitable. It may have had oceans of liquid water. It may have had a relatively thin atmosphere, similar to Earth's. But something happened. Something fundamentally altered Venus and made it uninhabitable. Scientists debate what that something was. Was it the bombardment that transformed Venus? Did the late heavy bombardment deliver so much energy to Venus that it accelerated a runaway greenhouse effect? Did the bombardment cause Venus to lose its water and develop the thick carbon dioxide atmosphere we see today? Or did Venus transform through some other process, perhaps related to internal volcanism or the proximity to the Sun? Venus is closer to the Sun than Earth, and as the Sun's luminosity increased over time, the habitable zone where liquid water could exist moved outward. Venus may have gradually transitioned from habitable to uninhabitable as solar heating increased regardless of the bombardment. The truth is, Venus's transformation remains partly mysterious. What is clear is that Venus today bears the scars of an ancient violent past, and the bombardment contributed to the conditions that transformed Venus into the hellscape it is. Earth, despite being pummeled, survived. The bombardment did not destroy Earth. Earth did not vaporize. Earth did not lose its capacity to host life. In fact, the bombardment may have delivered something crucial to Earth. Water. The inner solar system, where Earth formed, should have been too hot for water ice to accumulate during planet formation. The young sun's heat would have vaporized water ice before it could be incorporated into the growing terrestrial planets. There is a boundary in planetary systems called the frost line, the snow line, the water ice line. Inside this boundary, it is too hot for water ice to exist. The frost line in the young solar system was positioned somewhere in the outer portion of the asteroid belt, farther out than Earth's orbit. Earth formed inside the frost line. During Earth's assembly from planetesimals and protoplanets, any water ice would have vaporized before being incorporated into the growing world. Earth should not have much water, and yet Earth today is covered with water. Oceans cover more than 70% of the surface. Water is the most abundant substance in the biosphere. Earth contains so much water that the total volume of all oceans, all ice sheets, all groundwater, all water in the atmosphere combined totals roughly 1.4 billion cubic kilometers. Where did all this water come from? The answer may be the bombardment itself. The comets and planetesimals that fell on Earth during the late heavy bombardment came from the outer solar system, from regions cold enough and far enough from the Sun that water ice remained solid and incorporated into the bodies of comets and icy planetesimals. These bodies formed in the outer solar system, in the regions where the gas giants had formed or where they had scattered planetesimals during their migrations. They carried water with them, locked inside their structure, frozen solid, protected from the sun's heat by being embedded in rocky and carbonaceous material. As they fell on Earth, travelling across the inner solar system for millions of years after being scattered inward by the giant planet's gravity, the water was delivered. The bombardment was, in a sense, a delivery system. A system that brought water from the outer solar system to the inner planets. Each impact brought not just energy, but also volatiles, the light elements and compounds that evaporate easily and that are essential for life. But water was not the only thing delivered. These comets and planetesimals also carried organic molecules, complex carbon-based compounds, amino acids, the building blocks of proteins, nucleotides, the building blocks of DNA and RNA, polycyclic aromatic hydrocarbons, sugars, the chemical building blocks of life, meteorites that have fallen on Earth in the modern era, samples from asteroids and comets, contain significant percentages of organic material. Some carbonaceous chondrite meteorites contain up to 20% organic material by mass. These organics are synthesized in space, in the cold regions of the outer solar system, through chemical processes driven by cosmic rays and ultraviolet radiation. The bombardment may have seeded Earth with not just water, but also the chemical ingredients necessary for life to eventually emerge. The early Earth, receiving impacts from comets and asteroids rich in water and in organic molecules, was being inoculated with the chemical feedstock for life. Mercury, without an atmosphere and without sufficient gravity to retain delivered volatiles, could not keep this water. The water that arrived at Mercury vaporized or escaped into space, except for small amounts that may have become trapped in permanently shadowed craters near Mercury's poles, where temperatures are cold enough to preserve water ice. Mars, small and with less gravity than Earth, lost much of the water that was delivered. Mars had formed with relatively little water compared to Earth, and the bombardment added water. But Mars could not retain it as readily as Earth could. Much of the water that Mars received was lost to atmospheric escape driven by impacts, leaving Mars dry and barren. But Earth, larger, with stronger gravity, and with a developing atmosphere to help retain water vapor, could retain much of the delivered water. The bombardment was destructive on an unimaginable scale, but it might also have been constructive. It may have brought to Earth the very things that would eventually allow life to flourish. Water and organic molecules and energy all arrived together, delivered by the same cosmic violence that pummeled the inner solar system. Jupiter's role in this bombardment was profound and paradoxical. Jupiter is the largest planet in the solar system, a gas giant with a mass greater than all other planets combined. During the Nice model scenario, Jupiter's migration inward and then outward created the gravitational disruption that scattered the planetesimals. In a sense, Jupiter caused the bombardment. But Jupiter also eventually became the solar system's protector. Once the giant planets had completed their migration and settled into something close to their modern orbits, Jupiter's massive gravity began to protect the inner solar system rather than assault it. Jupiter's large size and strong gravity meant that objects in the inner solar system were no longer as vulnerable to impacts. New planetesimals and comets moving through the solar system were more likely to be captured by Jupiter than to hit the terrestrial planets. Jupiter, the agent of chaos during the bombardment, became the guardian against future bombardments. This dual role, destroyer during the migration phase and protector thereafter, defines Jupiter's relationship to the rest of the solar system. Without Jupiter's inward migration, the planetesimals would not have been scattered into the inner solar system and the bombardment would not have occurred. But without Jupiter's subsequent outward migration and its eventual settlement into its current orbit, the bombardment would have continued indefinitely, and the inner planets would have been bombarded so relentlessly that the development of habitability, let alone life, would have been impossible. Jupiter's dramatic early history had to happen for the solar system to reach its current configuration. The bombardment had to happen for Earth to receive the water and organic molecules it needed. The transformation of Jupiter from destroyer to protector had to happen for Earth to be protected afterward. It was not a planned sequence. It was the inevitable result of physics and gravity operating on the planets and planetesimals. But the result was a solar system capable of supporting life. This transformation from destroyer to protector is gradual. It did not happen overnight. But by the time the late heavy bombardment had ended, by the time the impact rate had dropped back to something approaching normal levels, Jupiter had already begun its protective function. As the migration of the giant planets continued and as they gradually settled into their modern orbits, the gravitational configuration of the solar system stabilized. Once Jupiter was in its current position, at 5.2 astronomical units from the Sun, its gravity became the dominant dynamic influence on the trajectories of small bodies in the outer solar system. New impactors, new comets and asteroids moving on orbits that might otherwise have led them toward the inner planets encountered Jupiter's gravitational influence first. Jupiter's massive gravity captured some of these bodies entirely, pulling them into orbits around Jupiter as moons or eventually into Jupiter itself. Other bodies were deflected. Their trajectories bent so sharply that they missed the inner planets, and instead went flying off into the outer solar system, or even out of the solar system entirely. Without Jupiter's gravity well drawing in impactors and protecting the inner planets, the bombardment might have continued longer, struck harder, made the inner planets even more hostile to life. Jupiter's massive presence in the outer solar system acts as a shield, deflecting and capturing objects that might otherwise threaten the inner planets. This is not something Jupiter does intentionally. It is simply a consequence of physics. But it has the effect of protecting the worlds where life can exist. Some scientists have suggested that the existence of a Jupiter-like planet in a solar system may be necessary for that system to develop complex life, because without such a planet, bombardments like the late heavy bombardment would occur repeatedly, making the development of life unlikely. If this hypothesis is correct, then Earth's existence as a habitable world with complex life may depend directly on Jupiter's protective influence. By around 3.8 billion years ago, the late heavy bombardment was winding down. The impact rate was declining. The planetesimal disk that had supplied the bombardment was mostly exhausted. Most of the remaining icy bodies had been flung either into the inner solar system or into the outer solar system or out of the solar system entirely. The giant planets had largely completed their migration and settled into relatively stable orbits. The solar system was still violent by modern standards, but it was no longer a war zone. It was still dangerous. Impacts continued to occur. Large impacts would continue to strike Earth for billions of years into the future. The current estimated rate of asteroid impacts on Earth is roughly one impact of 10 kilometers or larger every 100 million years. The dinosaurs learned how dangerous impacts could be 66 million years ago. But the overwhelming assault of the late heavy bombardment was over. The inner solar system had survived. Earth had been transformed by the bombardment, heated, impacted, reshaped, but not destroyed. The moon had been resurfaced repeatedly by impacts and now bore a heavily cratered face that would remain largely unchanged for the rest of its history. Mercury had been pummeled and transformed into a world of dense material and heavy cratering. Mars had been stripped of much of its atmosphere and had lost most of the water that had begun to accumulate on its surface. Venus had been subjected to impacts that may have contributed to its transformation into a hellscape. And perhaps, in being bombarded with water and organic molecules and energy, Earth had been given the gifts it needed to eventually develop life. And perhaps, in being bombarded with water and organic molecules and energy, Earth had been given the gifts it needed to eventually develop life. By around 3.8 billion years ago, the late heavy bombardment was winding down, not because the asteroids and comets had suddenly run out, but because the gravitational chaos that had driven them was gradually subsiding. The giant planets had completed most of their migration. Their orbits were no longer changing as dramatically as they had been. Jupiter had moved back outward from its in-attack position to something closer to its current orbit at 5.2 astronomical units from the Sun, having retreated from the inner solar system, where it had briefly dominated. Saturn had also migrated outward, pulled back by its gravitational interactions with Jupiter and the remaining planetesimals. Uranus and Neptune, having been scattered to enormous distances from the Sun by the disruption that followed the initial resonance, were gradually settling into more stable trajectories. The resonances that had driven the chaos, the gravitational locks that forced different orbital periods on the giant planets, were dissolving. The planets were no longer caught in the precise mathematical relationships that had amplified small perturbations into massive orbital changes. The planetesimal disk that had supplied the bombardment was mostly exhausted. Billions of small bodies had been flung either into the inner solar system or into the outer solar system or out of the solar system entirely, scattered to the winds of space by gravitational interactions with bodies millions of times their mass. What remained was a fundamentally reorganized architecture. The same planets, but in different positions. The same Sun, but no longer surrounded by the chaotic cloud of debris that had characterized the earlier era. The solar system had been remade, reordered, transformed from a realm of chaos into a realm approaching something resembling stability. The impact rate on Earth began to decline, not suddenly, but gradually, persistently, like a fever slowly breaking after a prolonged illness. Where impacts had been occurring multiple times per million years, the frequency dropped. A century might pass without a dinosaur extinction level impact, then 1,000 years, then 1,000,000 years. The background bombardment continued, of course. Smaller asteroids still struck the surface regularly. Meteorites still fell from the sky. The moon still accumulated craters, though at a much slower rate than during the peak of the bombardment. But the overwhelming assault, the relentless onslaught of massive impacts that had characterized the previous hundreds of millions of years, began to ease. The transition was not instantaneous. It took millions of years. But the direction was clear. Fewer impacts, less destruction, more stability, more time between catastrophes. The solar system was still dangerous by modern standards, still violent, still capable of sudden, catastrophic events. Impacts continued to occur. Large impacts would continue to strike Earth for billions of years into the future. 66 million years ago, an asteroid struck the Yucatan Peninsula and killed the dinosaurs. That impact released energy comparable to billions of nuclear weapons. The explosion created a crater 180 kilometers across. The impact triggered earthquakes, vaporized rock, sent tsunamis racing across oceans, threw dust into the atmosphere that blocked out the sun. It was one of the most destructive events in Earth's history. But even that cataclysmic impact was dwarfed by what Earth had endured during the peak of the late heavy bombardment. During the bombardment, impacts 100 times more powerful occurred multiple times per million years. The dinosaur killer was merely one of dozens of such impacts that would have occurred during a brief interval of the bombardment. The modern impact rate, estimated at roughly one impact by a 10-kilometer object or larger every 100 million years, represents a dramatic decline from the chaos of 3.9 to 4.1 billion years ago, when such impacts occurred perhaps 1,000 times more frequently. The transition from bombardment to relative stability was not instantaneous. Computer models suggest the transition took place over a span of perhaps 20 to 200 million years, depending on exactly how the giant planets migrated and how much material remained in the planetesimal disk to be scattered and ejected. Some models show a sudden spike in impacts, followed by rapid decline, a scenario where the bombardment peaked and then abruptly decreased as the giant planets moved into their stable orbits. Other models show a more gradual decrease, a scenario where impacts declined steadily over time as the planetesimal disk was exhausted. The evidence from moon rocks, with the clustering of impact ages around 3.9 billion years ago, with lunar samples showing evidence of being melted in impacts during this narrow window of time, suggests something closer to a concentrated bombardment followed by decline rather than a gradual tapering that continued unchanged for hundreds of millions of years. But the exact details remain uncertain, debated among planetary scientists who continue to refine their models, adding new data from asteroid missions and lunar studies, comparing them against the observations available from lunar samples and orbital data and crater analysis. The disagreement is not fundamental. The bombardment definitely happened. It definitely declined. The question is not whether, but how sharply and over what timescale. What matters, what is absolutely critical to understand, is that the bombardment did eventually end. The planetary migration that triggered it gradually slowed and stopped as the system settled into a new configuration. Jupiter's gravity eventually stabilized into a pattern, no longer dragging massive numbers of planetesimals inward in a constant cascade, no longer participating in violent scattering events that move billions of objects per year. Saturn's gravity no longer pushed outward against Neptune and Uranus with the same intensity, no longer driving their outward migration. The resonances that had amplified the chaos, the gravitational locks that had forced the planets into relationships that magnified small perturbations, gradually dissolved as the orbital parameters changed. The system found equilibrium. Not perfect equilibrium, not a state where nothing ever changed again, but an equilibrium stable enough that smaller bodies could maintain orbits for billions of years without being suddenly ejected or scattered into the inner solar system. An equilibrium stable enough for planets to cool and solidify, for crusts to form, for differentiation to complete. An equilibrium stable enough for life to eventually emerge in a stable-ish itself, for life to become not a temporary chemical accident, but a persistent feature of at least one world in the solar system. The inner planets that emerged from the bombardment were scarred, but intact, damaged, but still coherent, shaped by violence, but still capable of supporting worlds. Mercury, the closest planet to the Sun, looked like it had been through a war zone because it had been subjected to the most intense bombardment of any terrestrial planet because of its proximity to the region where planetesimals were most densely concentrated. The entire surface was covered with impact craters, countless craters, more craters than could be individually counted. Ancient craters, overlapped by newer craters, overlapped by even newer craters. The bombardment had literally resurfaced the planet multiple times, erasing old craters beneath new ones, then erasing those new ones in turn beneath even newer impacts. Large basins carved by kilometer-sized impactors scarred the landscape. Enormous depressions left behind when objects the size of mountains struck the surface at velocities of tens of kilometers per second. The largest of these basins, the Caloris Basin, is 1,550 kilometers across, larger than France, one of the largest impact structures in the entire solar system. It is larger than any terrestrial impact basin on Earth because Earth's plate tectonics have erased the evidence, have recycled the crust, have covered up the ancient scars with new rock. Mercury has no plate tectonics. It has no geological processes that obscure ancient craters. It has no erosion that softens the landscape and disguises the damage. The Caloris Basin is still there, fully visible to orbital cameras, still bearing the name and the memory of the collision that created it. And it is not alone. Dozens of other major basins scar Mercury's surface, each one representing a catastrophic collision of earth-shaking proportions. The bombardment did not just create craters on Mercury. It fundamentally shaped the planet's structure, altered its composition, heated it so intensely that the rock melted. Each major impact released tremendous energy, heating Mercury's crust, sometimes vaporizing material entirely, turning solid rock into superheated vapor. The cumulative effect of billions of impacts was to thoroughly remix Mercury's surface, churning through the crust, burying deep material on the surface, and bringing buried material up to be exposed. This created a complex landscape of basins, peaks, valleys, and escarpments, all jumbled together in a chaotic terrain, unlike anything we see on modern Earth. Mercury, after the bombardment, was not an intact planet with a few scars. It was a planet that had been pulverized, hammered, reshaped by cosmic violence, and somehow managed to remain a coherent body, held together by gravity despite the brutality of the assault. The Moon, closer to Earth, but smaller than Mars, experienced an even more intensive bombardment on a per-impact basis. The lunar surface too became covered with craters. The Imbrium Basin, created about 3.85 to 3.9 billion years ago, became the Moon's defining feature. 1,150 kilometers across, surrounded by concentric rings, the basin was filled with lava that flowed from the Moon's hot interior. The impact that created it was one of the last of the giant impacts. The energy released would have been unimaginable. The shock waves would have traveled through the Moon's interior. Material would have been ejected into space at velocities of kilometers per second. And yet after the impact, the Moon did not fall apart. It remained intact, held together by its own gravity, unable to be torn to pieces despite the titanic, unimaginable forces at work. Over time, gravity pulled much of the ejected material back down, or the material that was ejected with sufficient velocity escaped into space. And what was left was a moon bearing a giant scar that would never heal. That scar is still visible today, clearly visible from Earth orbit, a permanent reminder of violence that occurred nearly 4 billion years ago, never fading. Mars, smaller and farther from the Sun than Earth, experienced a bombardment that had more severe consequences for its long-term habitability. Mars is less than half the size of Earth by diameter, and only about 11% of Earth's mass. Each impact on Mars removed material from the planet's surface, heating it, vaporizing it, sending it into space. Mars lost atmosphere through these impacts, lost the protective blanket of air that had begun to accumulate. The young Mars, in the first few 100 million years of solar system history, had been developing a thick atmosphere, building up gases that would shelter any potential life. Volcanic activity released gases that built up around the planet, and a magnetic field protected the upper atmosphere from solar wind erosion. But the bombardment changed everything fundamentally. Large impacts heated the upper atmosphere, allowing gas molecules to escape at velocities high enough to overcome Mars's gravity. The heat provided energy that allowed hydrogen and lighter atoms to reach escape velocity, to break free from the planet's grip. Each impact that stripped away Mars's atmosphere also weakened its magnetic field through the energy released and the disruption of the core. And Mars lacked the mass and gravity of Earth. Mars was not strong enough to hold on to the light elements that were being blasted away, could not maintain a protective atmosphere through the onslaught. Over time, with impact after impact, Mars's atmosphere was depleted, reduced, stripped away. Reduced from something possibly similar to Earth's early atmosphere to the thin, tenuous thing we see today, less than 1% of Earth's atmospheric pressure. The bombardment contributed significantly to Mars's transformation from a potentially habitable world with liquid water and a thicker atmosphere to the cold, dry, barren desert we see today. Venus received its share of impacts as well. Venus today is a hellish world, hot enough to melt lead, with an atmosphere so thick and toxic that no spacecraft has survived on its surface for more than a few hours. The atmospheric pressure at Venus's surface is 92 times greater than Earth's atmospheric pressure. If you were standing on Venus's surface, the pressure would crush you as if you were underwater at a depth of nearly a kilometre. The temperature reaches nearly 500 degrees Celsius, hot enough to melt lead, literally, not metaphorically. The atmosphere is composed almost entirely of carbon dioxide with clouds of sulfuric acid. Rain falls on Venus, but the rain never reaches the ground. The droplets evaporate in the extreme heat before they can complete their descent. But Venus did not start out this way. Venus and Earth are similar in size. They likely formed through similar processes. Venus is only slightly smaller than Earth, and the two planets formed in the same region of the solar system, assembling from similar materials. In the early solar system, Venus may have been habitable. It may. I have had oceans of liquid water, water that could exist on the surface without immediately evaporating into space. It may have had a relatively thin atmosphere, similar to Earth's early atmosphere, composed perhaps of nitrogen and carbon dioxide, but not thick enough to create the runaway heat trap that exists today. But something happened. Something fundamentally altered Venus and made it uninhabitable. Scientists debate what that something was. Was it the bombardment that transformed Venus? Did the late heavy bombardment deliver so much energy to Venus that it accelerated a runaway greenhouse effect, heating the atmosphere to the point where water vapor accumulated in the upper atmosphere and was broken apart by ultraviolet radiation from the sun, the hydrogen escaping to space while oxygen was retained in the rocks? Did the bombardment cause Venus to lose its water and develop the thick carbon dioxide atmosphere we see today through some cascade of climate feedbacks, where loss of water meant less weathering of rocks, meant less absorption of carbon dioxide, meant more greenhouse heating? Or did Venus transform through some other process, perhaps related to internal volcanism, or the increasing luminosity of the sun over time? Venus is closer to the sun than Earth, and as the sun's luminosity has increased over billions of years, a process that continues even today, the habitable zone where liquid water could exist moved outward. Venus, originally positioned in this habitable zone, gradually moved outside it as the sun brightened. Venus may have gradually transitioned from habitable to uninhabitable as solar heating increased, regardless of the bombardment, unable to shed the heat that accumulated on its surface. The truth is, Venus's transformation remains partly mysterious, debated among planetary scientists, influenced by factors we fully understand, and likely by factors we do not. What is clear is that Venus today bears the scars of an ancient, violent past, and the bombardment contributed to the conditions that transformed Venus into the hellscape it is, whether as a direct cause or an amplifier of other processes already at work. Earth, despite being pummeled, survived. The bombardment did not destroy Earth. Earth did not vaporize. Earth did not lose its capacity to host life. In fact, the bombardment may have delivered something crucial to Earth: water. The inner solar system, where Earth formed, should have been too hot for water ice to accumulate during planet formation. The young sun's heat would have vaporized water ice before it could be incorporated into the growing terrestrial planets. There is a boundary in planetary systems called the frost line, or the snow line, or the water ice line. Inside this boundary, it is too hot for water ice to exist. The frost line in the young solar system was positioned somewhere in the outer portion of the asteroid belt, farther out than Earth's orbit. Earth formed inside the frost line, During Earth's assembly from planetesimals and protoplanets, any water ice would have vaporized before being incorporated into the growing world. Earth should not have much water, and yet Earth today is covered with water. Oceans cover more than 70% of the surface. Water is the most abundant substance in the biosphere. Earth contains so much water that the total volume of all oceans, all ice sheets, all groundwater, all water in the atmosphere combined, totals roughly 1.4 billion cubic kilometers. Where did all this water come from? The answer may be the bombardment itself. The comets and planetesimals that fell on Earth during the late heavy bombardment came from the outer solar system, from regions cold enough and far enough from the Sun that water ice remained solid and incorporated into the bodies of comets and icy planetesimals. These bodies formed in the outer solar system, in the regions where the gas giants had formed or where they had scattered planetesimals during their migrations. They carried water with them, locked inside their structure, frozen solid, protected from the sun's heat by being embedded in rocky and carbonaceous material. As they fell on Earth, travelling across the inner solar system for millions of years after being scattered inward by the giant planet's gravity, the water was delivered. The bombardment was, in a sense, a delivery system, a system that brought water from the outer solar system to the inner planets. Each impact brought not just energy, but also volatiles, the light elements and compounds that evaporate easily and that are essential for life. But water was not the only thing delivered. These comets and planetesimals also carried organic molecules, complex carbon-based compounds, amino acids, the building blocks of proteins, nucleotides, the building blocks of DNA and RNA, polycyclic aromatic hydrocarbons, sugars, the chemical building blocks of life, meteorites that have fallen on Earth in the modern era, samples from asteroids and comets, contain significant percentages of organic material. Some carbonaceous chondrite meteorites contain up to 20% organic material by mass. These organics are synthesized in space, in the cold regions of the outer solar system, through chemical processes driven by cosmic rays and ultraviolet radiation. The bombardment may have seeded Earth with not just water, but also the chemical ingredient, ANTS, necessary for life to eventually emerge. The early Earth, receiving impacts from comets and asteroids rich in water and in organic molecules, was being inoculated with the chemical feedstock for life. Every impact was a delivery. Every collision was a gift wrapped in catastrophe. The early Earth, as the bombardment was winding down around 3.8 billion years ago, was beginning to show signs of habitability. The surface had cooled enough for liquid water to exist persistently, at least in some regions and for at least some periods of time. Oceans had formed, covering perhaps a significant fraction of Earth's surface. The oceans were not pure water. They contained dissolved minerals from the rocks of Earth's crust, salts and silicates leached out of the rocks by the interaction with water. They contained organic molecules delivered by the bombardment, carbon compounds that had travelled across the solar system, embedded in the structure of comets and asteroids. The atmosphere, shaped by volcanic outgassing and the delivery of volatiles through impacts, was beginning to establish a composition that could support chemistry far more complex than the simple hydrogen-helium atmosphere of the very early Earth. Perhaps the early atmosphere contained nitrogen, fixed by lightning and volcanic processes, nitrogen that would become essential for the development of amino acids and proteins. Perhaps it contained methane and ammonia produced by chemical reactions in the ocean and atmosphere, organic compounds that would later become building blocks for more complex chemistry. Perhaps it contained carbon dioxide released by volcanism and by the chemical weathering of rocks, a powerful greenhouse gas that would help retain heat on the young planet. Some scientists argue that the earliest evidence of life on Earth comes from around 3.8 billion years ago, which is when the bombardment was winding down, when the impact rate was declining, when the worst of the violence was fading. Other scientists argue that life emerged even earlier, perhaps 4.1 or 4.2 billion years ago, which would mean that life was emerging even as the bombardment was still intensifying, even as the impacts were still numerous and violent. If that is true, then life on Earth began its history being bombarded by asteroids and comets, born into chaos, forced to adapt to circumstances of extraordinary violence. The earliest life would have been subjected to extreme stress immediately after its emergence. Microscopic organisms would have had to survive the heat of impacts, the shock waves propagating through the oceans, the vaporization of water as massive objects struck the surface. Imagine life so fragile that a single large impact could boil away all the oceans on Earth, vaporizing the water and sending it high into the atmosphere, where much of it would be lost to space, where the ultraviolet radiation from the sun could break apart the water molecules. Life that emerged during this time would have had to be tough beyond any modern comprehension, beyond nothing we can imagine today. It would have had to exist in spaces protected from the bombardment, refuges where the violence could not reach. Perhaps deep underground, in pores within rocks far below the surface, where the impact-generated heat and shock waves might not penetrate deeply. Perhaps in the oceans, but in the deepest trenches, where the thermal energy from the planet's interior could provide insulation against the surface, temperature changes caused by impacts, where the water pressure could shield organisms from the worst effects of the bombardment. Perhaps near hydrothermal vents on the ocean floor, where chemical energy could be extracted from the interaction of hot volcanic rock and seawater, providing a stable food source that did not depend on sunlight or organic molecules delivered from space, a chemosynthetic ecosystem thriving in places where impacts could not reach. The earliest life, if it existed during the bombardment, would have been resilient and resourceful and adapted to extreme conditions beyond our modern experience, more rugged and more adaptable than any organism alive today, shaped and hardened by survival under the most hostile circumstances that Earth could provide, tested by violence and selection pressure unimaginable. Jupiter, largest of all the planets, played a paradoxical role in this entire sequence. A role that explains why the solar system developed the way it did, and why habitability became possible on Earth. During the migration phase, when Jupiter moved inward toward the Sun and then outward again in the grand tack, it caused the bombardment through its gravitational interactions with the planetesimal disk. In a sense, Jupiter was the primary cause of the violence that devastated the inner solar system. But after the migration was complete, after Jupiter had settled into its current position at 5.2 astronomical units from the Sun, it became a shield, a protector, a guardian. Jupiter's massive gravity meant that new impactors moving through the solar system were more likely to be captured by Jupiter than to hit the terrestrial planets. Large objects, comets, asteroids, planetesimals still moving through the solar system after the main population had been scattered were more likely to encounter Jupiter first, attracted by its enormous gravitational well. Jupiter's gravity would capture them, sending them spiraling into the planet itself, or deflect them into new orbits that miss the inner planets, or fling them out of the solar system entirely at velocities so high that they would never return. Without Jupiter's protective influence, the bombardment would have continued longer and struck harder. The inner planets would have been subjected to continued assault, continued impacts, continued heating and disruption. The development of habitability, let alone life, would have been far more difficult, or perhaps impossible. Without Jupiter to clear away new impactors, to act as a cosmic garbage collector, the inner solar system would remain in a constant state of bombardment. Jupiter was the destroyer during the chaos phase and the protector after. The same planet, playing opposite roles at different times, first the agent of chaos and then the guardian of stability. What emerged from the violence was not merely survival, but transformation. The solar system that existed at the end of the late heavy bombardment was fundamentally different from the solar system that had existed at the beginning. The planets had migrated from their original positions, moved by gravitational interactions, scattered by resonances, reorganized by chaos. The asteroid belt had been largely emptied of its original inventory, reduced from a much more massive disk to the relatively sparse collection we see today. The planetesimal disk had been scattered throughout the solar system or ejected into interstellar space, its material flung outward to the Kuiper belt and Oort cloud, or inward to collide with the terrestrial planets, or sent flying out of the solar system entirely. The near planets bore the scars of billions of impacts, their surfaces reshaped by collisions, their interiors heated by the energy of bombardment, their compositions altered by the addition of extraterrestrial material. But they also possessed something new. Earth possessed water and organic molecules, gifts delivered by the very bombardment that threatened its existence. Mars possessed a thinner atmosphere, but still some capacity for liquid water to exist on the surface, and still the possibility that life might have emerged before the atmosphere was stripped away. Venus possessed the seeds of a runaway greenhouse effect that would eventually transform it into the hellscape it is today, a potential that may have been triggered or accelerated by the bombardment. The Moon possessed impact basins and highlands and a complex geological history written in stone, a record of impacts so numerous and so violent that it would have seemed impossible that any world could survive. Mercury possessed a heavily cratered surface and a dense iron core that had somehow remained intact through the violence, compressed and shaped by billions of collisions. The bombardment did not create these differences among the planets, but it amplified them. It shaped them. It accentuated some characteristics and dampened others. It left marks on the planets that would persist for billions of years into the future. The oldest rocks on Earth that we have access to, zircon crystals from Western Australia dated to 4.4 billion years ago, show evidence of the bombardment in their structure. They show evidence of being heated by impacts, of being partially melted and recrystallized in ways that only happen when enormous energy is released suddenly. They show evidence of liquid water on Earth's surface as far back as 4.3 billion years ago, indicating that despite the bombardment, despite the chaos, oceans existed. Life itself, if it truly did emerge during the bombardment, left almost no trace behind. The oldest possible evidence of life on Earth comes from carbon isotopes in rocks dated to 3.8 or 3.9 billion years ago, the Isua greenstone belt in Greenland. These isotopes, with their unusual ratios of carbon-12 to carbon-13, might indicate biological processing of carbon, the signature of organisms that preferred to use the lighter isotope in their biochemistry. Or they might not. They might simply reflect non-biological chemical processes. The evidence is subtle. The interpretation is debated extensively among geobiologists and paleontologists. But the possibility that life emerged while the bombardment was still ongoing is profoundly important because it would reshape how we understand the resilience of life. It would mean that life did not require a safe, stable world to get started. It would mean that life emerged in a war zone and not only survived, but thrived there. It would mean that the earliest organisms on Earth had to be tougher than anything we see alive today, adapted to an environment of constant disruption and regeneration. The legacy of the bombardment extends to the present day, visible in multiple ways, encoded in multiple mediums. It is written in the craters on the Moon, craters that will persist essentially unchanged for billions of years into the future unless another bombardment occurs. The Moon has no geological processes to erase the ancient craters, no plate tectonics to recycle the surface, no weathering to smooth the terrain. What happened 3.8 billion years ago remains visible today, a record of violence frozen in time. It is written in the composition of meteorites that fall on Earth. meteorites that carry the chemical signature of the early solar system. When a meteorite falls on Earth, scientists can analyze it and learn about the composition of the material that formed the solar system, material that has not been greatly altered since the planets formed. It is written in the structure of Earth itself, in the layered interior with a dense iron core sitting at the center, a rocky mantle surrounding that core, and a thin crust at the surface. This layered structure tells a story of internal differentiation, of heavy elements sinking to the center and light elements rising to the surface, a process that requires melting and energy. The bombardment shaped not just the surface, but also the interior. The impacts heated Earth profoundly, contributing to the internal differentiation that created the core and mantle structure. The impacts delivered material that would become part of Earth's composition, adding to the planetary mass and changing the chemical makeup of the world. The impacts delivered the water and organic molecules that would eventually become the basis for life, gifting Earth with the chemical feedstock for biology. The bombardment was destructive on an unimaginable scale, but it was also constructive. It built the solar system that we see today. It created the conditions for habitability. It delivered the chemical ingredients necessary for life. And once the bombardment ended, once the solar system had settled into relative stability after hundreds of millions of years of chaos, once Jupiter had shifted from destroyer to protector, the stage was set for something extraordinary to emerge on Earth.